Howdy, this is Mr. Potter. Today we're going to start talking about limits. So we're going to talk about two ideas here. One is what is a limit, and two is what are the properties of limits, how we can use those properties to evaluate limits. Now this is going to be the first of a few days we're going to be talking about limits. So let's go ahead and get to the idea of what exactly is a limit. The idea here is that I can figure out what f of x is if I know what f of x is for a particular function. Like if I know that f of x is x cubed, I clearly can evaluate f of 3. That's 27. But if I had some other function here, like g of x equals x squared minus 4 over x minus 2, the question is what happens at g of 2, because I can't substitute 2 into here. 2 makes this expression undefined. So the question is, if I were to look at the graph of this, though, I notice that my graph tends to look like this. And something happens here at 2. I can't have a point at x equals 2. But what I've got here is I've got a hole that has a certain property. I can get as close as I want, and I end up getting as close as I want to this value of 4. So the question is, why is this 4? How do I get to that point? And that really is the concept of a limit. So I want to start with the actual formal definition of a limit. So what happens is we say the limit of f of x as x approaches c is equal to some value L. And what this means is for all real epsilon greater than 0, there has to exist a real delta value that's also greater than 0, such that for all x with 0 less than the absolute value of x minus c is less than delta, we know that f of x minus our L value, the absolute value of that, must be less than e. And of course, this is all Greek to me. So let's talk about what this looks like from a picture. So I'm looking outside. I've got this window, and I know that something's happening to my function at a particular point. I'm kind of hidden here, though, because I see the frame of the window, the vertical bars and the horizontal bars, and they're kind of blocking what happens. The question is, does my graph really go through that point? Am I defined somewhere else for this particular value of x? Or do I just have a hole and I don't have a graph point defined where x equals c? Because what I'm saying is that as x approaches c, my graph's y value should approach L. And the idea is no matter how narrow my window is, there's got to be a value around L such that everything in this domain must also be contained within this range, with the possible exception of what happens exactly at C and exactly at y equals L. So when I'm looking at this, I have no idea what's exactly happening at my graph. I could have a continuous function. I could just have a hole here when x equals c. But that hole is going to be at a very specific position. And the question is, how do I determine that position? And the way that I do this is through several methods, one of which deals with some parent functions that we're quite familiar with. I want to start with the parent function y equals 1. This is the parent function for my polynomial of degree 0. And of course, the graph for y equals 1 is just going to be a horizontal line that passes through the y-intercept of 1. The other parent function I want to talk about is y equals x. And this is just our parent function of a linear. So I've got a line with slope of 1 that passes through the origin. And the idea here is if I'm looking at my constant function at y equals 1, then if I were to ask what is the limit as x approaches some value c of my function, well, as x approaches c, no matter what x is approaching, my y value is approaching 1. And similarly, if I were to look at this, the limit as x approaches c of my function x, well, as x approaches c, y is equal to x, so my y value also is going to have to be c. And so these are the two properties that I'm going to be starting off with. The idea that I have the limit as x approaches c of 1 is going to be equal to 1. And the limit as x approaches c of x is going to be c. So with these two given parts, I can come up with a whole family of properties of limits. So I'm going to start with assuming that the limit is f of x as x approaches c is equal to L. And g of x approaches m as x approaches c. So the question is what happens to some functions that depend on both f and g. So for example, let's say I want to find the limit as x approaches c of the expression f of x plus g of x. And what we find is that this is equal to my limit L plus my limit M. And it really doesn't matter if I'm adding or subtracting these expressions. The sum of the functions will give me the sum of the limits. The difference of the functions will give me the difference of the limits. And I could just as easily make this f of x plus f of x, and I would get L plus L, which is 2L. So the idea here is that if I have the limit as x approaches c of some number times f of x, I should get that same number times L. Whether that number is 2 or 10 or 1/2, multiplying by a scalar factor, my function ends up multiplying my limit. So this is kind of like when we adjust the amplitude of a sine function. The idea is that instead of going from -1 to 1, we're going from negative a to a. And in the same vein, instead of just multiplying a function times the scalar, I could also look at multiplying my function times another function. So I could look at f of x times g of x. And that should give me L times M. So these are some of our basic things that we can do arithmetically with our limits of f of x and g of x. And we'll talk about how to use these in just a few minutes. But there are a few more properties that I want to talk about. If f of x and g of x are the same thing, then what I'm really doing is I'm squaring f of x. And if I'm squaring f of x, I should be squaring my limit. And in fact, I can actually take f of x and raise it to some power. Let's say the r over s power. And that should be equal to L raised to that same r over s power. Provided that L to the r over s power is real. Because I don't want to run into the situation where I'm going to take the square root of a negative number, or if I'm going to take the fourth root of a negative number. I can run into that situation if my expression is not real. So I do need to have this caveat, and this takes care of it for me. Provided L to the R over S power is real, this limit of raising any function to the R over S power would give me that limit. And similarly, I can easily multiply two functions. I do have to be careful, though, when I'm dividing two functions. So if I was to take a look at f of x divided by g of x as x approaches c, then this is going to be equal to L over m, provided that m is not equal to 0, because I'm not allowed to divide by 0. That affects my domain. So these are some of our basic limit properties, things that we can do. Given a function, we can manipulate the function through addition, subtraction, multiplication by a scalar, multiplication by a function, division, and raising a power. So let's take a look at a sample limit here. I've got the limit as x approaches 3 of the expression x cubed minus 3x plus 6. Now, I know that this is going to be equal to the limit as x approaches 3 of x cubed minus the limit as x approaches 3 of 3x plus the limit as x approaches 3 of 6. This is one of the properties we had for addition and subtraction of limits, that the limit of a sum is equal to the sum of the limits. And we notice that whenever we had a power, I could really find the limit as x approaches 3 of x and raise that limit to the third power. This is one of the properties of limits that we were talking about on the previous page. This property of raising to the R over S power. Because x is approaching 3, this will end up being an actual value, a real number. And this 3 is a scalar, so I could actually pretend this is 3 times the limit as x approaches 3 of x. And this is really 6 times 1, so I can treat this as 6 times the limit as x approaches 3 of 1. And this is why I stress those limits from our parent functions earlier in the video. The limit as x approaches 3 of our linear function is just going to be 3. so this ends up being 3 cubed, or 27. So this limit is also 3, and I end up with 3 times 3, which is 9. The limit as x approaches 3 of my constant function 1 is just 1. So this becomes 6 times 1. And so I'm adding a 6 to the expression. So I have 27 minus 9, which is 18, plus 6, and so I get 24. And this technique of using those properties of limits, they work in this example, and in fact they'll work for any polynomial. So we end up with this idea here, is that if I have the limit as x approaches c of some polynomial, all I'm really doing is substituting that value into my polynomial. And so that's a pretty powerful statement. The thing is, if I have a polynomial, I don't have to go through this rigorous procedure. I can just do the direct substitution, because it follows from the property of exponents, the property of coefficients, and the properties of addition and subtraction, that I should get a numerical limit as long as my value is defined. Function. In here, I've got my graph of the function y equals sine of x over x. And I've got it on the domain from pi over 2 to negative pi over 2. Excuse me, from negative pi to pi, and on the range from 0 to 2. And what I'm noticing here from the graph, it certainly appears that my function approaches the value of 1 as x approaches 0. And so we say that the limit as x approaches 0 of sine of x over x is equal to 1. Now, at this point, this is not something that we're prepared to prove. We'll talk about this later in the book. But right now, this is definitely something that we need to memorize, because we can use this as an additional tool in our repertoire of how to solve limits. So this is definitely something we need to memorize. And the reason we need to memorize it is because questions involving this limit show up repeatedly on the AP exam. And so I want to go through a couple of examples of So let's say I have the limit as x approaches 0 of x times the cotangent of x. What I'm going to do is I'm going to represent this in a slightly different manner. I've got the limit as x approaches 0 of x times cotangent is cosine of x over sine x. So all I've done is rewrite cotangent in terms of its constituent functions. And I can just as easily rewrite x as x over 1. So I'm really taking this limit, but multiplication is commutative. It doesn't matter in which order I multiply. So I could just as easily write this as the limit as x approaches 0 of x over sine x times cosine x over 1. Because I can easily just switch these two terms here. Now I'm looking at this and I remember that the limit of a product is equal to the product of the limit. So I can deal with the limit as x approaches 0 of x over sine x and the limit of cosine of x over 1 as x approaches 0. And this limit is actually pretty well defined. 0 is actually in the domain of cosine. So I can just substitute. And the cosine of 0 is 1. This, however, is really the limit as x approaches 0 of 1 divided by sine x over x. It's really the reciprocal of this function. And we mentioned that this limit does exist, because the limit of a fraction should be equal to the limit of the numerator over the limit of the denominator, so long that the limit of the denominator exists, and it is 1. So what we actually end up with is we end up with 1 times 1, which is 1. So this has a pretty straightforward limit. I've got this limit here where I'm evaluating the limit as x approaches 0 of sine of 3x over sine of 4x. So the first thing I want to do is I want to rewrite this as the sine of 3x over 1 times 1 over the sine of 4x. And what I'm going to do is I'm going to use a little trick here. I'm going to multiply times a clever form of 1. I'm going to multiply times x over x. But again, I'm going to use that property of the commutativity, that multiplication doesn't care in what order it's multiplied. So I'm actually going to multiply this x times this 1. And I'm going to multiply this x times that 1. So this is really the sine of 3x over x. And this is really x over the sine of 4x. The limit as x approaches 0. Now, this would be wonderful if my angle matched my denominator. Sadly, it doesn't. But I can use this same clever form of 1 multiplying by 3 in the denominator and multiplying by 3 in the numerator. And similarly, I can make this angle match this by multiplying by 4 in the numerator and 4 in the denominator. And I use the property of limits. So this is going to be the limit as x approaches 0 of sine 3x over 3x times the limit as x approaches 0 of 4x over sine 4x times the limit as x approaches 0 of 3/4. And at this point, I've got 3 really nice limits. This limit here is sine of theta over theta as theta goes to 0. So this limit is really 1. This limit here is very similar to what we had to do with the reciprocal up here. And the reciprocal of 1 is 1. This limit here is a constant. This is a constant function. So as x approaches 0, this y value is always going to be 3/4. And so I end up with 1 times 1 times 3/4, which comes out to 3/4. So there's some interesting relationships between the answer we get and the way that our original problem is phrased. It's definitely something to look at. So what we've done here is today we've talked about how to manipulate a limit through substitution, through the properties that we already know from our parent functions, and through the properties of limits that we've talked about today. And we've also introduced one limit that we definitely have to know, like the back of our hand, the limit of sine of x over x. last thing I want to touch on today is, well, when does a limit not exist? And there are a couple of situations that we've seen before where a limit does not exist. I could have a situation like y equals 1 over x. This is our reciprocal function. And I notice that anytime that I have a vertical asymptote, this definitely is not going to be some hole that could be filled later. So vertical asymptotes are definitely a situation where a limit will not exist. Similarly, I could look at something like y equals the square root of 4 minus x squared. This is really the top part of a circle. So if I take a look at this graph, I know I've got the top part of a circle of radius 2. But if I try and take a look at this from a window standpoint, I really can't say that I have a limit here because I have nothing to compare on the right side of my graph. Primarily because the right side of this graph isn't part of my domain. So if I have a restricted domain, and the last situation where we might have that a limit would not exist is if I have what we call an oscillating discontinuity. We'll talk more about discontinuities when we talk about continuous functions. But if I was to have a function like the sine of 1 over x, and I was to take a look at this graph, I know that at 2 pi sine is 0. I know that at pi sine is 0. But then I've got this situation where the closer I get to the origin, the more times this function is going to go up and down, and up and down, and up and down. It's going to oscillate an infinite number of times the closer I get to the origin. So the question is, do I hit here at 1? Do I hit here at negative 1? Or do I hit somewhere in between? And the fact is there is no one spot where we can be considered to hit. There is no one spot where the hole is. What I've actually got here is a alternating discontinuity. So these are three situations where we can have where a limit does not exist. Now, just because we have situations like this doesn't mean that we can't treat these situations. We can't talk about them from a restricted standpoint, maybe talking about it from one side or the other, because I definitely know what's happening where my domain exists. I just run into the problem of not knowing what happens where my domain does not exist. Here my domain of 0 does not exist. Here my domain of 0 does not exist. And so what we're going to talk about the rest of this week is we're going to be talking about how to deal with limits when I can't do a direct substitution, when these properties of limits fail me. And so that's where we're headed. So once again, this is Mr. Potter. Thank you for watching. Have a great day.